All right. So, good afternoon. My name is Kevin, and I'm a SOKENDAI PhD student. And today I'm going to talk about the optically detected galaxy clusters in the AKARI NEP field. Although it is a little embarrassing to talk this after the wonderful talk from Yentings. All right, so these are my collaborators. They are all AKARI NEP team's members. So this talk, I will not focus on these people. I will talk to the people who are not familiar with AKARI field. Well, so at the very beginning, I would like to give you some ideas to this work. I would say that this might be the most important slides in my presentation because you are not going to remember all the detail I'm going to talk about later. So the goal is very simple. Is we want to find galaxy clusters in the AKARI NEP field. And our method, we are very ambitious. We want to find as many galaxy clusters as possible. So we base on only the positional information of galaxies, which is the coordinate and redshift. We are not going to use any assumption of the color or luminosity function or density profiles. So as a result, we have some cluster candidates, and also we perform some analysis to them. But still, we have some reliability problems of the clusters at high redshift. All right, so this is my outline. The outline is very normal. I will start with the introduction and with the summary and covering the analysis result discussion. And because the result is not complete yet, I also raise some future prospect to do. Okay, so the introduction is why the galaxy clusters is important. They are important because they can be widely used in many studies. They provide a good laboratory for astronomy and cosmology studies. For example, here I raise some examples here. The first one is it can be the environment for the galaxy evolution study. And the second one is it can be used in study the BAO in cosmology. And also, we can use galaxy clusters to study the high redshift galaxies because cluster can be the computational lens. Then, what we know that the cluster is important now. Then, how do we detect them? The first, um, these three are the most frequently used methods. The most directly way is using the X-ray observation because the intra-cluster medium themselves emits the X-ray light because they are hot, consist of a hot gas. And also the famous XZ effect, we can use a microwave to observe clusters, or more precisely the CMB. And the third one is the optical galaxies. As the previous talk and as my talk, my work, we are going to use the optical galaxies to find galaxy clusters. So usually optical galaxies where we need some information of the clusters, or we need to use some based on the sequence of the galaxy clusters, or we need to base on the density of the galaxy clusters. So previous work from the Ogrisans HSC collaboration, they are using the red sequence. But in our method, we are going to use the density. The advantage of using optical data is because we can select a large number of galaxy clusters. Now let's move on to the analysis part. So as I just mentioned, we are ambitious. We want to use only HSC data. And all the HSC data are detected in 5 sigma in all the HSC bands. And we also remove some extended sources using the parameters called extendedness in the HSC pipeline. Here is a remark that we are not using the AKARI data here, although this work is in the AKARI NEP field, because using the infrared data might have a selection bias to the infrared galaxies. And to use the positional information, the photometric redshift is required. To calculate the photometric redshift with using the only 5 band is not reliable. So we also include some other multi-wavelength data like CFH TCU band data, HS's narrowband data, and Spitzer's near-infrared data. So here is the result of the photo Z. The method and the model's parameters are same as the whole et al. 2020s. And these photo Z are calculated by the SED fitting using the FAR. The result is fairly, we cannot say that it's very good, but it's barely satisfactory. Like we have a dispersion of 0.06 and catastrophic rate at 9%. We also remove the stars from galaxies according to the best fitting stellar models. So after we got all the positional information, we can start to find galaxy clusters. Then we know that a cluster is dense and it has high number density. So one way is we need to define the local density of every galaxies. So the way we use is the 10th nearest neighborhood. And also a cluster is abundant. So we have to combine them into a group, and we need to define who of the galaxies are the member of the clusters. So we use a friend-of-friend algorithm to create groups. So here I show what is the 10th nearest neighborhood. So assuming all the smiling face are the galaxies. So if we looking at this case, the red galaxy, then we calculate the distance to it. The first nearest neighborhood, I define it as itself, and the second one, third one, fourth one, and so on. Then the 10th nearest neighbor is this guy. And this distance is the 10th nearest distance. We use this distance to define the local density. And in other case, for the blue one, its 10th nearest neighbor is this, and the distance is this. So these two galaxies has different local densities. And later now I'm going to show you what is the friend-of-friend algorithm. So assuming that all of these are galaxies, and one important parameters of this friend-of-friend algorithm is the linking length. That is the length determining all the galaxies within this length are defined as a friend. So let me start at these galaxies. So the circles are plotted in the linking length. And for these galaxies, they have friends. And after the friend is defined, they continue to find new friends by the old friends, like this way. So eventually, a group will be created in this way. So here I show the summary of my method, but I'm not going to explain all the details here. Just remember that we have the photos example, and we calculate the local density of these galaxies, and we define the overdensity. And later we apply the friend-of-friend algorithm to this overdensity to define the cluster candidates. So here I'm going to show my results. Here is I pick up two examples the clusters. And yeah, and these images are the HSC's optical images. And we do have some known X-ray clusters in previous research. And in total, there are 8. And 4 of them are detected through our method. This result is not so bad because we found that the undetected cluster, they are all Rosas cluster, which has very old detection. And also they are very faint in X-ray, or they are very nearby. So another important result of this work is the color magnitude diagram. We plot the color magnitude diagram of the clusters members in red and the field galaxy in the redshift bins in blue, in black dots. And we want to cut some of the cluster showing the red sequence features like this. And we want to cut the red galaxies. So we empirically find a definition that using the 70 plus 20 times redshift percentile of the field galaxies is a good cut, just empirically. And I give a tier of clusters based on the red galaxy fraction. So for this one, tier 1 cluster looks very promising to have a red sequence. And another case is like tier 2 clusters, maybe it has a potential red sequence, and the tier 3 clusters might have a lot of contaminations. So further studies about the tier of clusters is we show that the fraction of tier 1 and tier 2 cluster is decreasing with the redshift. So it looks like that our cluster candidate is not very reliable at high redshift. And because I'm running out of time, I have also do the false detection, and the conclusion here is the same as the tier analysis, that the reliability at high redshift is not so good in our research. So now we are going to planning to do the completeness analysis and calculate the richness and modeling the red sequence. Probably in the future, we can do more studies about the X-ray temperature and the velocity dispersion of the cluster candidates. So I will stop here with my summary. Thank you very much.
Thank you. I have a question on Slack. In the friend-of-friend algorithm, the linking length is angular length, and what is the typical value of that?
Oh, linking length. Okay, so we determine the linking length based on the angular distance of the, we calculate the 10th nearest distance, and based on this distance, we fit this distance with a function of arctangent functions, and determine using this as a linking length. So its scale is at the, you can see that it's a megaparsec scale from 0.1 to about 0.3 megaparsec.
All right, thank you. Another question from ENT.
Do you just use the photo Z as spec Z, or how do you account for the photo Z uncertainties?
It is a very difficult question. I don't know how. Sorry.
Oh, maybe I can answer. Because Kevin is using the same density values as my research. So when we calculate the density, we use the spec Z if it's possible. And we use the photo Z if only photo Z is there. and then we account for the photo Z errors in the redshift bin where the densities are calculated. So we select galaxies for a certain galaxy. The redshift bin where the density is calculated depends on the redshift photo Z uncertainty. So that's how we calculate density.
You have a photo Z PDF.
Yes.
Okay, we are running out of time. You can keep discussing locally or also on Slack. Please try using Slack for remote participants. Okay, thank you very much, Kevin.
Thank you very much.